Our next speaker is Federico Adolfi.
Yeah, so hi everybody. I'm going to be talking about let's first, yeah. I'm going to be talking about ongoing work with Todd Wareham and Iris van Rooij on the computational complexity of segmentation. This is an attempt to get a formal grasp on the properties of segmentation as a cognitive subcomputation and to evaluate existing assumptions against what we can prove mathematically. That said, because I'm mindful that there's probably a diversity of backgrounds in the audience, I'm going to try to do this informally without any of the theoretical computer science jargon. And I'm going to treat this just as an invitation for you to read the paper. Okay, so in part one, I'm going to be introducing segmentation as a subcomputation that shows up in multiple cognitive domains. And then I'm going to look at a generic model of segmentation that we build and later submit to computational complexity analyses. And and after that, we will look at the computational assumptions that have been taken on board regarding the search space size and the fundamental hardness of the problem of segmentation. And in part two, I'm going to present the results of combinatorial and computational complexity analyses that test these assumptions more formally. And finally, I'll discuss briefly some of the possible takeaways from this exercise. Yeah, I think that's all. And let me begin by giving you a general idea of what we mean by segmentation. Segmentation is thought to be a core subcomputation in many cognitive capacities, such as speech recognition, music cognition, statistical learning, action parsing, event processing, and many more. It's the sub-process in any of these domains and at any given processing stage that takes a sequence representation where we have a number of possibilities for how we can group things, and outputs a good segmentation scheme according to some domain-specific criterion. So Ann Cutler wrote a whole paper about this a long time ago in the context of speech comprehension, which I only found out about this paper months after our paper was accepted. But I will use it here to illustrate some of the intuitions that have been taken on board as computational assumptions more broadly. This text right here is just to tempt you to go and read this paper because it's a special paper. It's a very aesthetically pleasing one. But the gist is in red, and she's talking about how in written text, there's clear boundaries between words, whereas in spoken text, the input is continuous. So she concludes that part of listening must involve an operation whereby input is segmented. But before we get into the assumptions about this process, let's quickly build up a model of segmentation as a generic subcomputation beyond speech comprehension. So in this schematic of the formal model that we build, we have some sequence as an input, let's say belonging to the domain of speech or music or visual scenes. But remember that this can be at any processing stage. And the segmentation subcomputation sits within a broader capacity shown at the top. Again, for example, speech recognition. And therefore, we also have domain-specific processes. For example, processes that compute over segments. This is shown at the top right. And for example, this could be a decoder for the recognition of the content of a segment. And part of the output of this domain-specific process can be used to guide the search for a solution to the segmentation problem itself. For example, the decoding confidence according to some internal model. And as an output of the whole computational problem, we ask for a useful segmentation scheme that is an optimal or good enough segmentation of the sequence with respect to some domain-specific process. That's a grouping that's ideal, for example, to recognize the parts of the whole. So what are the computational assumptions about segmentation processes across domains? We find that there are assumptions about hardness, the sources of this hardness, sources of complexity, and what constraints and corresponding cognitive strategies are useful to tackle this complexity. So at one point, Cutler again writes, the findings, as this summary explains, at once can vindicate the order of the problem and the hearer's sense of ease. For though speech must be segmented, yet the data plainly indicate that rhythm in the input makes segmenting speech a breeze. So the essence of this, that the problem is hard, so there must be some constraint that the humans take advantage of to make it tractable. This thing captures a pattern of intuitions about segmentation that shows up in the literature over and over, and it has been adopted as an informal assumption across various domains. So for instance, one can find these kinds of statements in papers, and I'm paraphrasing here. Speech recognition is challenging. Segmentation requires inference over an intractably large space, or event processing is not a simple problem. The system must segment a continuous input into discrete units that are appropriate for downstream tasks. And the template, the general template that captures this assumption about computational hardness is an informal reduction that says that some cognitive capacity is hard precisely because it involves segmentation. And let's unpack how this reasoning works. First, it's assumed that segmentation is not harder than a given cognitive problem. And this is by conjecture because segmentation is conjectured to be a subroutine of this broader cognitive problem. For example, segmentation is thought to be a subroutine of speech comprehension. Then in the second step, there's an assumption that segmentation is hard, and we're going to see in a moment why people think it's hard. And as the final step, the conclusion is that the cognitive problem is itself hard because it inherits the hardness of segmentation. And here we're really interested in the second step where the assumption is made. So what about the assumed causes of this hardness? We can find plenty of examples of this, of intuitions for this. And again, I'm paraphrasing. People say, where should we place the boundaries, considering every combination would be computationally inefficient, or the problem is enormously complicated by the presence of so many segmentation candidates, which basically comes down to assuming that the combinatorial explosion involved in the size of the search space is responsible. So to expand a little bit, there's a number of boundaries that can be placed to produce candidate segmentations, and the number of choice combinations grows very fast with increasing sequence length. So maybe as a consequence of taking these beliefs on board, the effectiveness of certain constraints on the problem has been taken for granted. So for example, people will say, sort of describing a research program, the aim should be to identify the mechanisms that reduce these computational burdens by reducing the number of candidates. And this is a recurring pattern, again, which is captured by this structure. So you have to imagine a certain domain. There are behavioral, neural, and environmental regularities that suggest constraints that presumably make the problem easier if we can grant the system mechanisms to use them. And this idea has motivated empirical programs trying to find such regularities. Again, Cutler describes the emerging picture very elegantly. She says, so the picture that emerges is that rhythm as exhibited in the verse forms of a language can effectively predict those procedures which, assuming that their use is not inhibited, allows us to declare the segmentation problem licked. So let's recap these intuitions turned assumptions. There are assumptions across domains about hardness, the sources of complexity, and the solutions to reduce this complexity. So we can capture this with this phrase: tasks involving segmentation are fundamentally hard due to combinatorial explosion, so we must find the constraints on search space size that make the problem easy. And here we enter the picture by looking at this from the point of view of theoretical computer science. Specifically, we use analytic combinatorics to characterize how the search space grows, and complexity theory allows us to capture what it means for a task to be fundamentally hard. So let's take a look at the results. We begin with the search space size. We will examine formally 3 popular constraints that have been assumed to make the search space of segmentation manageable. And they are inspired by behavioral, neural, and environmental regularities, which I don't have time to go into here. But the basic idea is that bounding the possible size of the segments that are allowed in a candidate segmentation somehow makes the problem easy to solve. And these constraints would correspond to the strategies that cognitive systems must use. So here's the first set of results we prove. For unbounded segments, it's well known that the search space size indeed grows very fast with the size of the sequence. But then we also prove 3 other constrained versions of the problem, lower bounding the segment size, upper bounding the segment size, and combining those 2 constraints. And we see that these constraints, neither individually nor combined, make the issue go away. Now, these proofs might give the impression that the problem is indeed fundamentally hard, but this is not the case. This just proves that applying these constraints cannot immediately buy tractability. So what can we say about the hardness of the problem itself? Rather than how large its candidate solution space is, we're now asking how hard the space is to search in a more fundamental way. And for this, we need to turn to the technique of reduction. So I have no time here to dive into the details of the proof. So I'm going to walk you through a proof by animation. So what we need to show is that segmentation can be efficiently reduced to a problem whose properties we understand, and this will allow us to deduce the properties of segmentation itself. And in doing so, we're going to translate the problem of from the sequence domain to the graph domain. And incidentally, there, the structure of candidate solutions is going to be made visible. So, okay, it works. I will walk you through this with an example sequence of length 4, which you see now on the top right. We first take all the possible segments of length 1 and construct a vertex for each of those. We will also keep them around just for the purposes of understanding the proof. Then we do the same for segments of length 2, and so on for other segments, length 3, length 4. And that's all the vertices. And then for each pair of vertices, we check the corresponding segments. And if they overlap, we build an edge between them. And here I'm highlighting one by one those pairs that have some overlap. Now the graph is complete. We have our vertices and edges. And now the structure of the problem is made more transparent. We can see that a candidate segmentation must correspond to an independent vertex set because they should be disconnected. And moreover, it must also correspond to a dominating set because it shouldn't be possible to add any more segments to a full segmentation. So any candidate segmentation will correspond to what's called an independent dominating set. And a feasible solution is just an optimal solution or good enough solution among these candidates. Okay, so we can translate the problem of segmentation to the problem of finding optimal vertex sets for this class of graphs. But you might ask, how is this helping? Okay, so let's put up our formal reasoning to see how it compares with the pattern of assumptions we saw before, and hopefully it will make it clear. So we have an efficient way to go from instances of segmentation to instances of this graph problem. And this allows us to infer that the segmentation problem cannot be harder than the graph problem. And here, crucially, the graph problem is easy or efficiently computable, and we know this by independent proof. So therefore, we can conclude that segmentation is easy in this sense. And note here that in our proof, we did not have to use any of the constraints that the literature assumes that are necessary to declare the problem licked or declare the problem solved. So, okay, as a summary of the results, I'm coming to an end. Is the search space of segmentation large? Yes, it is large. Is it easily reduced by empirically motivated constraints? We saw that it doesn't seem to be the case. But we can ask, is the space is fundamentally hard to search? But we also saw that that is not the case. So how hard is segmentation? Well, contrary to common assumptions, it can be easy even in the absence of constraints. So a few takeaways from this exercise. The results suggest that empirical programs based on the assumption of hardness might not be building on a solid theoretical and formal foundation. But of course, our results are not meant as the final word on the complexity of segmentation. Our proofs rather provide a scaffolding to assess cognitive models that involve segmentation as a subcomputation. And this is crucial because our intuitions about computation can be, and often are, wrong, and it's important to verify them formally. So some thank yous and some recommendations. I'd like to thank the reviewers of this work and my co-authors, Iris van Gooy and Todd Wareham. If you would like to read more from them, you can check out the first paper. If you liked this approach and want to see a much more advanced use in the domain of communication, you can check out Laura van der Prak's Flash talk. And if you like the meta-theoretical aspect of this work, you might like Olivia Guest's paper on meta-theoretical calculus in cognitive science. Thank you for listening, and I'm happy to take questions if there are any.
We have a question from online. I'm going to ask our technical chair to read this one out.
Thank you. So it has been asked that I can see this working for text that is complete, but how do you do segmentation when consuming a stream of text?
For text that is complete. Oh, okay. I guess the person asking the question is bothered by the fact that the analysis sort of takes a chunk of text and then you segment that chunk of text. But we proved that it's possible to have efficient algorithms for this problem, and this opens up also dynamic programming algorithms that will work on online text, and then the question will become a question of accuracy, right? You will be able to process ongoing text as long as you have some tolerance for the accuracy, but it's not really a problem. It's just our analyses have this aspect of analytic simplification in the sense that it turns out not to matter substantially.
Hello, so I have a question. How do you determine the units when doing the segmentation, the basic units, and how to deal with a continuous speech that there's no discrete boundary between units?
Right. So our model is meant to be much more general than that. So the properties that we uncover here are going to apply at any processing stage that you have some segmentation process, right? So if you imagine that at the peripheral at the peripheral stage of the auditory system, you have some form of discretization. Let's say you have at least 400 discrete units per second. Some people believe this, that it's much more than this. Then the properties will apply to that case. But then if you imagine that you're going to be working with a phoneme as a unit, right? Then the analysis will work on that too. Like the segmentation model that we propose is what we call a computational level model in the MAR sense. So these particular details are more algorithmic, and once you make more commitments about at what level you're pitching your model.
Just a quick question, and we've got 1 minute. I found your first set of results that adding constraints on the number of units you consider doesn't make a difference quite surprising. Could you say something a little bit more about why that's the case? Give us the intuition.
Yeah, they were surprising to me too. I was expecting to get the tractability immediately with some of those. And one reason is because we assume that the capacity has to scale to arbitrarily large inputs. And this is something that people challenge all the time, right? It's this way of thinking about capacities as very productive. So these particular constraints that bound the size of the segments will not solve that problem. But if you actually introduce other types of constraints that bear some time invariance, so for example, if the system knows somehow how many parts the segmentation should have, this is time invariant, right? Because it will scale whether I'm speaking slowly or fast. If I know how many parts I should be able to extract from the sequence, then this will scale with time and we'll get rid of the problem. But the constraints that we tried don't have this property. So, but so to answer your question more directly, it is counterintuitive.
Cool,
Okay,
thank you.
thank you.